Welcome back. In this video, we're going to look at the life cycle of the sun. So about 4.6 billion years ago, there was a dark molecular cloud in the Milky Way galaxy, and large stars in the dark molecular cloud began to explode as supernova within a few million years. And then the formation of the sun was triggered by the supernova explosions or explosion, which sent out a shock wave. And just to appreciate the magnitude of a supernova wind, hurricane is 0.07 kilometers per second. Orbit of the Earth around the sun is 30 kilometers per second. When it first explodes, the wind is 30,000 kilometers per second. But some scientists think that the wind speed was about 30 kilometers per second when it impacted the dark molecular cloud that formed the Earth. So why a supernova? Well, it's because there's nickel-60 in meteorites in the solar system. And if there was nickel-60, then there must have been iron-60 at some point. And iron-60 is a short-lived isotope produced by supernova. So it must have been produced by a supernova shortly before the formation of the sun. And it would have been within a distance of 0.9 light years of the cloud. So once the cloud contraction was triggered by a supernova, there was slow contraction for a long time. And then there was an ionization phase where the gases were ionized, and that causes them to suck in energy, and that allowed the cloud to contract very fast for a short period of time. And then after the dramatic collapse of the ionization phase, the contraction continued for millions of years until the star reached the main sequence phase. So let's look at the ionization phase in more detail. As cores contract, the cloud core that became the sun, the protosun, they gradually heat up to about 10,000 Kelvin, which is same as 10,000 centigrade. And at 10,000 Kelvin, the nuclei and electrons separate, which is ionization, and form a plasma, and this absorbs the energy of contraction, so there's no resistance to collapse. So during what was a decade of catastrophic collapse, if you want to call it that, the core shrank from the diameter, the cloud core shrank from the diameter of Jupiter's orbit to the diameter of Mercury's orbit. So it wasn't as small as the sun, but it was getting close. And once that ionization contraction phase ended, the core was about 200,000 degrees Kelvin because the energy, the gravitational energy in the large cloud was converted to heat energy in this small core that formed. And if the inner part of the core was 200,000 Kelvin, the surface of that protostar, the protosun, would have been about 3,500 Kelvin. And even though the surface did emit visible light, it was redder, but it was still visible light. It would have been absorbed by the molecular cloud envelope still surrounding it. So that's why scientists need to look in the infrared range to see these forming protostars. So let's look at the sequence of contraction, and we can see that on the Hertzsprung-Russell diagram. And this is the sun. This would be a star twice the size of the sun, 5 times the size of the sun, and so on. So scientists can model the contraction phase for each size of star. And so they know that the sun followed this, I don't know if you can see it clearly, but this yellow line here. And there were 5 phases. The ionization collapse phase took 10 years, and that's the point at which it reached 3,500 degrees centigrade, and it was over 100 times brighter than the sun. But then as the size of the sun continued to drop for the next 10,000 years, the luminosity dropped by 100 times. And then C, the luminosity is continuing to drop. Here's the luminosity over here So as the size contracts, even though the temperature is increasing in this direction, the brightness of this protostar is decreasing because its size is decreasing. So at point C, it enters the Tauri phase, which is very unstable, and there's flash heating and so on, until about 1 million years. And then for 9 million more years, the star continues to contract until it reaches 10 million degrees in the core, and that's when nuclear fusion begins. So it had existed for 10 million years before there was nuclear fusion. All the energy came from contraction. Then it's here, and it became hotter, and so it became more luminous for a short period of time. But then it continued to contract, and it reached the main sequence line, which is where it will remain for 9 billion years. But it didn't reach the main sequence line for its first 30 million years. We can also look at this graphically. So here's the catastrophic collapse phase A, 10,000 years. And then here's the period where it contracted from 10,000 to 100,000 years. And then C, it enters the T Tauri stage from 100,000 years to 1 million years. So this is the unstable period. There's the disk here, but the planets haven't started forming within it. And then here's the period from 1 million years to 10 million years. Planets have basically formed, not completely. The disk is still unstable for about 200 million years, but at least the planetesimals have formed and are crashing into each other by this time. So now let's look at the main sequence phase. Different sizes of stars have different energy transfer characteristics. For example, a very large O star has convective heat transfer on the inside, meaning there's circulation, and that's carrying heat outward. And then they have radiative heat transfer, yellow, in the outer part of the star. Whereas the sun does not have convective heat transfer on the inside, it just has radiative heat transfer. So there's not a lot of cycling of hydrogen from the outer to the inner core. But then there is convective heat transfer in the outer part of the sun. But because there's not a lot of hydrogen transfer into the core, that means the sun's life is somewhat shorter. Whereas small stars like M stars, they have convective heat transfer. So they're continually circulating hydrogen into the core, which is the fuel. So they have, not only are they burning very slowly because they're small, but they're also circulating hydrogen into the core, which is why they last so long. The large stars burn so hot that they burn out in a few million years. The sun, like I said, will burn out in about 9 billion years. Then M stars will not burn out in any conceivable time. Okay, one of the advantages of the sun and other stars, many other stars, not all stars, is that the sun has a relatively stable temperature. You can imagine what would happen if the sun's temperature increased, and decreased by like 10%. But what happens is when the sun becomes hotter, the pressure pushes the sun outward, and so there's less density and pressure in the core, and so that slows down the nuclear fusion. And then when it becomes colder, gravity starts pushing into the core, causing it to be denser and increasing the nuclear fusion. So this is like a natural equilibrium where there's always a balance between gravity and pressure and nuclear fusion rate. And the essential message here is that the temperature of the sun remains almost constant. Now let's look at the 9 billion years of the sun's main sequence phase. So during the initial phase of the sun decreased in luminosity. That would be the energy transfer to the Earth also. So during this first few billion years, the sun was very cold, which is why scientists are surprised that there was liquid water on Earth during the first few billion years of Earth's existence. but there was. And so that's called the faint young sun paradox, which we'll talk about in chapter 7. And then the sun is gradually heated up. Here we are 4.5 billion years after the beginning, and it's going to keep heating up. And so here's global warming over. We don't have to worry about this global warming because it takes billions of years. So timescale isn't a problem. Unlike the other type of global warming where the carbon dioxide concentration is increasing quickly. We'll see you next time.